Now? Great.
Yeah, so the first talk will be by
Hello, everybody. Thank you, Xavier, for the nice introduction. My name is Zacharias. I'm currently a Marie Curie postdoctoral fellow. Okay, mouse. I'm currently a Marie Curie postdoctoral fellow at the University of Rennes, and today we're going to talk about the special displacement method. So in the special displacement method, it's an alternative approach to incorporate the effect of electron-phonon coupling in first principles calculations. So what we do here, we rely on adiabatic non-perturbative supercell calculations, and we actually displace the nuclei in the supercell to capture the effect of electron-phonon coupling. So here's a short lecture summary of my today's lecture. First, I will introduce non-perturbative approaches to electron-phonon coupling and anharmonicity. So we also talk today about anharmonicity. I will give a short recap for phonons and also introduce the normal coordinate transformation, which is quite central for today's lecture. And then I will discuss how we can go from the stochastic framework using a Monte Carlo integration to perform like the calculation, the supercell calculations, to the deterministic framework, to the point that we can use only one configuration to capture thermodynamic properties. And then I will introduce the theory of the special behind the special displacement method, and finally go to the self-consistent and harmonic special displacements. At the final part of my talk, I will talk about applications or potential applications. So in the literature, we can compute electron-phonon properties either using perturbative or non-perturbative approaches. One can, of course, use EPW, which you have been learning so far, or Rabini to compute the electron-phonon matrix elements with density functional perturbation theory within the small unit cell. Or other approaches include to compute electron-phonon properties non-perturbatively. So some implementations there is in BAS, the ZG code, which I'm going to talk today, path integral molecular dynamics, or like molecular dynamics relying on classical mechanics. So in these approaches, we indeed displace the nuclei. I'm going to talk now about these displacements. Also we have several methodologies that someone can compute anharmonic phonons, temperature-dependent harmonic phonons. Here I like put the codes of Alamo, TDEP, which relies on molecular dynamics, SHA, which is a stochastic non-perturbative approach, and also the ZG method, which relies on the special displacement method. So in these methodologies, the theory behind is the self-consistent phonon theory. And we again displace nuclei in supercells, and we either calculate higher order interatomic force constants explicitly or not. So a short recap for the phonons. We first rely on the harmonic approximation, and we expand the potential energy surface up to second order in nuclear displacements. So the linear term here goes away because we are at static equilibrium, so the forces are essentially zero. And we want to determine, like particularly, these second order coefficients of the potential energy surface with respect to nuclear displacements. So here, the P index indicates the unit cell we are in the supercell, K is for the atom index, and alpha is the Cartesian direction of displacement. So phonons have been introduced by Professor Giannozzi on Monday's lecture. So today I'm just giving a very quick recap. So we have the potential energy surface up to second order, the expansion, and we want to evaluate the interatomic force constants, which are essentially the derivatives of the Hellman-Feynman forces with respect to atomic displacements. And for evaluating the dynamical matrix at every Q point phonon wave vector, we need to do a Fourier transformation. And we evaluate the dynamical matrix using this equation. Here, the M represents the masses of the atoms. Then we can diagonalize the dynamical matrix and obtain information about the phonon frequencies and the phonon polarization vectors. For polar materials, we have to also include a non-analytic term induced by long-range interactions, dipole-dipole interactions. And this is the expression for the dynamical matrix. And here we have Z, the Born effective charges, and epsilon is the high-frequency dielectric constant. So how can we determine nuclear displacements? In Born-Oppenheimer adiabatic molecular dynamics, the nuclear displacements have a tight dependence, and we need to evaluate them by solving the equation of motion using classical mechanics. In non-perturbative approaches that I'm going to talk today, we have to use, again, adiabatic the adiabatic, within the adiabatic framework, we can obtain the nuclear displacements using the linear normal mode coordinate transformation. So here, the nuclear displacements are obtained by this scaling factor from the masses. So mk is the mass of the atom, and m naught is the reference mass, which we take the proton mass. And here the summation runs over all phonon modes. Is the phonopolarization vectors, x nu is the normal coordinates. So we're going to determine this expression for displacing our nuclei deterministically. If we assume that we can apply a smooth Berry connection to the phonon polarization vectors, then we can introduce an extra variable, which is the signs of the phonons. So these signs can, of course, be either plus or minus 1 and need to be determined. Another variable that we need to determine is basically the amplitude of the normal coordinates. So we are going to see how we can determine these two variables using the special displacement method today. One equation that I would like to introduce as like a nice homework for you would be to be able to go from the real space representation to the normal coordinate representation. For example, for this Taylor expansion of the potential energy surface. So if you use this normal coordinate transformation and the sum rule for the phonon polarization vectors, and also for the derivative of the displacements, one can demonstrate that we have a one-to-one correspondence for each term in the normal mode representation and the real space representation. The reason I gave this example is because it's a good exercise for you to understand what's going on with these non-perturbative supercell approaches. Of course, here the observable, here we have put the potential energy surface, but the observable can be anything, either a thermodynamic observable, the observable determined by electron-Phonon coupling, and so on. So here it can be the band gap, the imaginary part of the dielectric function, or the conductivity, for example. So here I use the example from Feliciano's lecture, the slide about diamond, where it shows the effect on the electronic structure if we displace the atoms along a particular phonon mode. So here we drop the summation essentially because we are doing it only for one phonon mode, and Feliciano chose an amplitude for the xn equals to 0.015 angstroms. And this is actually the terms coming above zero order is essentially the correction you have on your electronic structure given by the red curve here. Today, we are gonna actually show that we have the way to displace all the atoms along all phonon modes deterministically, so and also capture these coefficients properly, all right? So all non-perturbative approaches, the main aim is to evaluate the physical observable at temperature T. And this is the thermal average of the observable, which can be written as a trace over the complete set of eigenstates of the Hamiltonian, weighted by the standard Boltzmann factor, and Z is the partition function. So if we replace the observable with the transition rate between an electronic state alpha to a final electronic state beta and expand the trace, we can write, basically, we can obtain this expression as a canonical average, and the summation here runs over the final nuclear states. This is actually the common goal of all non-perturbative approaches. Here I introduce a few references where people, they actually use different methodologies to compute temperature-dependent properties. One can use path integral molecular dynamics using the Feynman representation of quantum mechanics. One can do ab initio molecular dynamics, where we solve the equation of motion using classical mechanics. Other people, they do even more sophisticated approaches. They do path integral for the nuclei, and with quantum Monte Carlo for the electrons, those approaches are quite expensive and involved, so they have been applied only for small molecules. Some other approaches involve important sampling Monte Carlo, where we draw these normal coordinates we discussed before from a multivariate Gaussian distribution, and we will see it later. And then it's a special displacement method where we choose deterministically the displacements and the signs, so we produce a configuration where we can evaluate thermodynamic properties. Other supercell approaches include finite differences and thermal lines, which is another very efficient methodology. So what is the special displacement method? And we call the configuration that we obtain after that a ZG configuration. So we displace the atoms away from their high symmetry positions, which are static equilibrium, so forces at zero. We displace them away from their high symmetry positions, and we obtain a representative snapshot of the system at thermal equilibrium. So why is it useful? So if we want to evaluate everything using perturbation theory, sometimes it might involve a very complex theory. or even the implementation, the coding, might be even more complex. In addition, when we have anharmonicity in the potential energy surface, again, the maps are becoming even more involved. Also, in perturbative approaches, we have to compute explicitly the Phonon matrix elements. We need to do linear interpolation. And usually, the truncation in the perturbative approaches is up to second order in nuclear displacements. So we are missing electron multi-phonon effects. So terms beyond second order in perturbation theory. Why is it useful compared to molecular dynamics? In molecular dynamics, we usually have to wait for the equilibration stage, and we are missing also the quantum nuclei effects, and sometimes the computational cost can be prohibitive depending on the supercell size. If we use Monte Carlo approaches, we have a risk to hit a faulty configuration, and sometimes we need to go like an enormous number of configurations to compensate for the error coming from the faulty configurations. Here, we have a strategy to avoid any faulty configuration and get a very good representative one to evaluate electron-Phonon properties using supercell approaches. And I like to describe the special displacement method like the Alexander the Great. So all these problems I described before are like the Gordian knot. And Alexander the Great said, what cannot be resolved, it is cut. So I consider it as a quick method to evaluate temperature-dependent properties. Here I will talk a little bit about Phonon-assisted optical absorption and temperature-dependent band gaps, which is something that you can do with the special displacement method. I'm going to go through details about Phonon-assisted optical absorption, which have been given by Professor Kubakis on Wednesday lecture, and Dr. Taiwari will also expand on this on Saturday. So here, what I want to stress is just in this work by Manos and Nofsinger, what they have calculated here is the absorption coefficient of silicon, but to match the experimental absorption onset, they had to rigidly shift the spectra. And this comes as no surprise because inside the delta function, we see that the Concha-Magen energies do not have any temperature dependence. In this example here, in this whole Martine-Blatt theory, the temperature dependence comes outside from this expression, from the Bose-Einstein occupations. So by increasing the temperature, you just increase the absorption intensity. You don't redshift the spectra. A theory which is consistent for evaluating temperature-dependent band structures and accounting for the energy level renormalization of the electrons is called the Allen-Heine theory. So here is this expression, essentially the perturbative expression, and we have the fan self-energy term and the Debye-Waller corrections to the band gap renormalization or the energy level renormalization. And this equation is quite famous. It has been implemented, like it has been used several times in the literature, and here I list a few of the references that are actually using this method successfully to evaluate temperature-dependent band gaps. Here I use the example of silicon from the amazing work from Samuel Ponce in 2015, where it shows basically the effect of zero-point motion on the electronic structure. And here we see that the valence band maximum goes up in energy, while the conduction band bottom lowers in energy. And this will lead essentially to the closing of the band gap. And if we use higher temperatures, this closing will be even more prominent. And if we think in terms of optical absorption, we will capture correctly the absorption onset if we insert this correction inside the delta function, essentially. But a consistent theory to account both for temperature-dependent band structures and for assisted optical absorption is the Williams-Lux theory. And its starting point is the Herzberg-Teller rate, which I provide here. The summation here runs over all final nuclear states represented by chi. P is for the optical matrix elements between an initial electronic state alpha to a final electronic state beta, and delta is the delta function that ensures energy conservation. Here we have the joint electron nuclear states represented by E beta M, all right? And for evaluating this object, it's computationally very demanding because you have a lot of transitions between all nuclear states. What do we do to get rid of this complexity? We need to use the same classical approximation and replace the joint electron nuclear energies with the adiabatic potential energy surface. Okay, and this approximation is okay if we assume that the final available states for transition have large quantum numbers, and based on the Born correspondence principle, we can replace these energies and we can treat them as continuous variables. So basically, if we replace with the adiabatic potential energy surface, we have no longer this M index involved, and we can perform the summation over the nuclear wave functions using the closure relationship and end up with this nice expression here. Then we can take the thermal average of this object, and if we apply the harmonic approximation and write the wave functions as a product of quantum harmonic oscillators, and also use the Mikler's formula, it's a formula that simplifies basically the computation and gives you this multivariate Gaussian integral, we can actually obtain the transition rate at finite temperatures. Here, these Gaussians, basically they have a width sigma, where the sigma is given by the mean square displacement of the atoms, where L is the 0-point amplitude, and N here is the Bose-Einstein occupation factor. So if we want to make some contact with DFT, we just can't simply subtract the potential energy surface of the excited state with the ground state, and for an extended system, here we can get the energy difference between the constant states of the occupied and unoccupied states. And then this allows us basically to compute the dielectric fraction at finite temperatures. And for simplicity, we use the independent particle approximation, but here the dielectric fraction is agnostic of the approximation. Someone can use a BSC calculation to evaluate the dielectric fraction. Still, the same equation applies. So what is the interpretation of this expression? It's a Monte Carlo integral. So we draw these x nu coordinates that enter our displacements in the normal coordinate transformation. We draw it from a multivariate Gaussian distribution, and we evaluate the spectra for a variety of configurations, and then we take the average, and we do that until we obtain convergence. And we actually used the Williams-Lux theory and the Monte Carlo integration to evaluate the optical absorption of silicon. And here we see that without introducing any displacements, we capture the direct part of the spectrum of silicon. And we see that we are like below the direct gap, we have essentially no transitions. While the experiment, you see, it absorbs down to 1 electron volt. If we account for electron-phonon coupling using the Williams-Lux theory, we can capture correctly indirect transitions and capture the correct absorption onset. Now I comment on the configuration of sampling, which is actually the key for today's lecture. So we found that if we are increasing the supercell size, we need less and less configurations to obtain convergence. And here, for an 8x8x8 supercell, we just need 6 configurations. But we found that one of those 6 gives the exact result. So we said, okay, might something happen here? Can we be able to predict one configuration a priori and compute temperature-dependent observables? So we did the maths, and actually here we have this multivariate Gaussian integration. We just simply take a Taylor expansion, as we have seen before, and we perform the integration. Because this integral is even, the odd terms will not survive, and actually the Gaussian integral over xn will give sigma n, all right? Sigma n squared. So we get the Williams-Lux expression, which is this object here. Now, suppose that we want to do the calculation with only one configuration. The trivial choice is to set the amplitude of the normal coordinates equal to this sigma. And then we get actually this expression. And I will discuss later why the linear terms anyway go away. So here we focus only on the second order terms, and we want to make this second order terms, this object, equal to the exact Williams-Lux object. So here we decide to put all the modes in a vertically order, and we alternate the size between plus minus, so that these cross-coupling terms that they are considered the error in our non-perturbative calculations, they cancel out. And indeed, we can demonstrate that in the thermodynamic limit, our one configuration will give the exact Williams-Lux dielectric fraction. And here, this is basically what determines the displacements that we discussed at the beginning. So we applied the concept of the one-shot method or the special displacement method to evaluate the phonon-assisted spectra of silicon and diamond. In both cases, we capture correctly indirect transitions, and we capture also correctly the absorption onset. So some deviations between theory and experiment are to be attributed basically to the fact that we use DFT and not quasi-particle effects or excitonic effects are not included in our calculations. Considering temperature-dependent band gaps, of course, we can use exactly the same methodology, and instead for the imaginary part of the dielectric fraction, we can evaluate the band gap, and here we use the example of silicon and molybdenum disulfide. We see that we have almost an excellent agreement with the experiment. So now coming to the maths and connection between non-perturbative and perturbative approaches. So these derivatives that we discussed before, which are the Taylor expansions, they actually have a meaning. They will, if you do Rayleigh-Schrodinger perturbation theory and you expand the wave function in perturbation theory and insert it in this object, you can get precisely the adiabatic version of the Hall-Bartinen-Blatt theory that drives phonon-assisted optical absorption. And also, if you do exactly the same for the case of Allen-Heine theory, for this term here, for the second derivative of the electron eigenenergies with respect to nuclear coordinates, you will get the adiabatic version of the Allen-Heine theory. So the drawback, the main drawback here is that we are in the adiabatic limit. So the phonon frequencies which usually enter in the denominators or the delta function, we don't capture them. So for example, for phonon-assisted optical absorptions, we don't have phonon emission or phonon absorption. We have an average fine structure. So this approximation can be okay if the phonon frequencies are well below the band gap. On the positive side, we can capture terms beyond second order, and we don't need to evaluate them explicitly. So that will include electron multi-phonon effects. And on top, we don't rely on the rigid ion approximation. So off-diagonal terms in the self-energy, in the real part of the self-energy, are included. So here it's a more compact expression for generating the special displacements. What we have done here is that we developed an expression in the reciprocal space. And the benefit for doing this in the reciprocal space is that, as you have seen, and as you have calculated phonon dispersions from density functional perturbation theory, now, using Fourier interpolation, we can have control of every phonon frequency and every phonon frequency and every phonon polarization vector, and we can generate displacements for an arbitrary size of supercell size. So we can generate a supercell size of 1,000, 1,000, 1,000. Of course, computationally, we cannot compute it, but the main point is that you can compute the phonons for a Q grid that you like, and then you can generate displacements for any supercell size. So this is actually the equation implemented in the DG code that you learn to use later in the afternoon. And here, basically, the code needs to determine the signs. And for determining the signs, we need to minimize, if you do the theory behind the special displacement method, you end up with an error function which depends on the signs. And we need to minimize this object in order to allocate the signs in an optimum way. And the code allocates the signs combinatorially till we find the error below a predetermined threshold. The nice thing with this minimizing this error, which is very fast, is that we don't rely on any extra DFT calculations, since all these quantities that enter this expression can be computed from density functional perturbation theory. So now coming to some other findings from the theory, these linear terms, if you have Q points that do not have, with no time reversal partners, these coefficients, they will reduce to 0. And also, these second order coefficients, for if the wave vector of the phonons is different, then again, these coefficients go to 0 by symmetry. And this actually simplifies a lot the procedure for finding, for allocating the optimum set of signs. And an example that I like to use for demonstrating the physical meaning of this configuration is basically the case for momentum resolved diffraction patterns. So imagine now if you have an electron beam that scatters inelastically from the sample, and you detect the beam, the intensity of the beam on the detector. What you will get is the so-called diffraction pattern. And here we use the example of black phosphorus, and we split the calculation into one phonon and multi-phonon. So here, with blue, we have the Bragg scattering intensity. So it's like we don't have any phonons, it's the elastic scattering part. And if we account for phonon in elastic scattering, we get the red area. And as I said before, we have one phonon and multi-phonon scattering. So if we sum the two, we get the all phonon diffuse scattering. So now coming to the special displacement method. So this is the scattering intensity formula. It's a very simple formula that we learn in our undergrad courses for solid state physics. And here is the summation running overall unit cells and overall atoms. And here we have the atomic scattering factor. And E here is the phase factor that involves in the exponent the scattering wave vector, the dot product of the scattering wave vector with information about the position of the nuclei. So if we don't have any special displacements, or if we don't have any displacement, and we have all the atoms at static equilibrium, we'll only get elastic scattering, the blue dots. If we include the special displacements, we get this diffraction pattern, which is actually equal, almost equal, to the exact result. And if we compare with the experiment, we get a very good agreement. So what's the physical meaning here? We can imagine that these displacements, they will get you a representative snapshot at thermal equilibrium, which will give essentially the best collection of scatterers that can, for example, reproduce phonon-inducing elastic scattering patterns. So band structure unfolding. Since we are using supercell calculations, if we want to obtain temperature-dependent band structures, we really need to unfold the band structure, which is folded in a smaller Brillouin zone, since we are using supercells. And for doing that, we project the wave functions of the supercell on the wave functions on the unit cell. And we can recover the band structure in the fundamental Brillouin zone. How to do that? We evaluate the electrospectral functions, and we need to evaluate the spectral weights, which are given essentially, which depend essentially on the plane wave coefficient evaluated for the supercell, given that the wave vector of the electron wave function in the supercell can be mapped to the wave vector of the electron wave function in the unit cell by a reciprocal lattice vector of the unit cell. So this is what is implemented in Math-Unfolded X, and it can be used with non-conserving ultrasoft or PAUP pseudopotentials, and someone can get these temperature-dependent band structures. And from here, you can evaluate the band gap renormalization. So coming to anharmonicity. How can someone explore anharmonicity using the special displacement method? So far, we have seen only harmonic cases: silicon, diamond, gallium arsenide are harmonic materials. But what happens if we go closer to anharmonicity? So if we have a weakly anharmonic potential, here, still the harmonic approximation can be good. But if we go to a strongly anharmonic case or double well potential, we see that the harmonic approximation will fail, and this will give unstable phonons. So in the literature, it's been almost 10 years that there are methodologies that allow you to compute temperature-dependent anharmonic phonons. TDEP is one methodology that relies on molecular dynamics. The SHA, which relies on stochastic non-perturbative approaches, so it uses a Monte Carlo integration. And Alamode, which actually relies on the explicit computation of higher order interatomic force constants. Can we upgrade the special displacement method? And can we do it for anharmonic systems? Yes, we can. And the benefit with the special displacement method is that we no longer have to deal with the configurational sampling. We can just generate special, like the configuration, one configuration, and we compute the interatomic force constants for that object. And we'll see how it works. So here, the harmonicity in all these codes that I have described and for the special displacement method relies on the self-consistent phonon theory. In the self-consistent phonon theory, we simply introduce an effective harmonic potential. And we want effectively to put all the corrections coming from an anharmonicity into this effective potential. So if we assume that we can introduce a perturbation, H prime, which includes all higher order anharmonic terms, which I write here, the correction to first order in perturbation theory, if we take the thermal average, will be exactly this expression. So that's why I told you at the beginning to know how to expand with respect to normal coordinates, the potential energy surface. And taking this integral, which is easy to perform, we have these corrections coming to like the effective Hamiltonian. So here we can include all first order diagrams, including the loop, which is the quartic diagram, and also which comes also in first in perturbation theory, right? So how can we obtain this effective potential? We need to minimize the free energy using a trial free energy, and based on the Gibbs inequality, this trial free energy should provide an upper bound of the actual free energy of the system. So by minimizing our trial free energy, we get closer and closer to the exact solution. So here, the free energy, we write it as a thermal average of the potential energy surface at finite temperature. But here, the expectation value is taken with respect to the eigenstates of the effective Hamiltonian. Here is the harmonic potential energy surface of the effective Hamiltonian and the vibrational free energy for the effective Hamiltonian. And if we expand it, we get this expression. So the aim here is to minimize the free energy of the system with respect to the interatomic force constants and put it equal to 0. All right? So we get the derivative of the free energy with respect to interatomic force constants. And basically, this is the derivative of every object entering this equation. And we can prove, the proof is straightforward, but it's very lengthy. We can prove that we can get this expression here. So in order to satisfy this equation here, we need to set the interatomic force constants at finite temperatures equals to the second derivative of the potential energy surface with respect to nuclear displacements. So we have to do that iteratively until we obtain self-consistency. And that ensures that we have minimized our trial free energy. So what's an effective potential? What is this effective potential that I've been talking about? So if we have a harmonic case, the effective potential will coincide with the true potential effectively, and we get the exact Schrödinger nuclear equation. However, if we have a double well potential, we try to fit a harmonic approximation to this double well potential so that it best describes the solution of the Schrödinger nuclear equation. However, for doing so, we have to start from an initial point. So we can either determine our initial point to be a harmonic approximation at the local maximum, but this will have unstable phonons, so it is not a good starting point. But we can also fit a harmonic approximation at the local minimum. This local minimum is usually defined by a polymorphous structure. And what I mean by polymorphous structure is a structure that has local disorder, which I indicate here, but on average and macroscopically, the structure respects the symmetries of the lattice. So the high symmetry structure will define a local maximum, and this gives unstable phonons. The polymorphous structure will effectively describe the ground state of the system. So we choose to evaluate initially the phonons from this ground state structure. So here is the recipe. We want to compute temperature-dependent effective interatomic force constants. And for doing so, we displace our atoms using the special displacement method. And we want to apply finite differences, but now not on the system at static equilibrium, but on the system at thermal equilibrium. And we want to do that iteratively until we obtain self-consistency. So this involves, first we compute the harmonic interatomic force constants of the polymorphous structure using finite differences. We enforce the symmetries, and we obtain an initial set to start the iterative procedure. Okay, this is the phonon frequencies and the phonon polarization vectors from the polymorphous structure. So indeed, here we get stable phonons represented by the red line for the polymorphous structure, while the green is the monomorphous structure represented representing unstable phonon dispersions. So using those initial set, we can generate special displacements. We compute the interatomic force constants using finite differences, and then we enforce the crystal symmetries to the temperature-dependent interatomic force constants, and by diagonalization, we can calculate temperature-dependent phonon frequencies and phonon polarization vectors. Then we repeat step 3 to 5 until we obtain self-consistency. And we found that if we do iterative mixing, the convergence for the iterative procedure speeds up a lot. Here is the convergence performance using the example of cesium-lead bromide. With green, again, we have the phonons for the monomorphous structure, harmonic approximation of the high symmetry system. We get a lot of instabilities. So cesium-lead bromide is a strongly anharmonic material. And then we get the phonons of the polymorphous structure, which is represented by the red line. And then we start doing the iterations. Here, the first iteration is the gray line, which is not quite visible here. And this is good, actually, because this says that even from the first iteration, we are almost converged. So with 2-3 configurations, so the configurational space is no longer a problem. So what's the problem is to do the calculations, but that's, if you have the computational power, you can do it. You get convergence. And this is actually for a 2x2x2 supercell. So the calculations here are not that involved. So you will see in the tutorial how you can obtain actually the phonon dispersion of cesium-lead bromide within half a day, basically. Then here is the validation of the methodology for the case of zirconium. Very good agreement with experiment. And also I validate the methodology compared to the state of the art, which is Alamode or TDEP or SHA methods for the case of strontium titanide capturing the temperature dependence of the transverse optical mode 1 and transverse optical mode 2. We see that all these methodologies, so the line here is for the T depth, is for the ALA mode, the circles is for the T depth, and the squares is for the SHA methodology. We see, and the diamonds is for the ASDM. So we see that in all cases, we have very good agreement with experiment. Another point that I want to stress is here, this slide, the message is twofold. First, okay, now we did the ASDM, we have our anharmonic phonons. We can use those anharmonic phonons with a special displacement method and evaluate anharmonic electrophonon properties. And this is the case of the band gap normalization of strontium titanite and cesium lead bromide. And the other message of this slide is that whether we use the high symmetry structure and we start the displacements from the high symmetry structure or the polymorphous structure. So with red is when we start the displacements from the high symmetry structure. So we see that for strontium titanite, we underestimate the band gap renormalization, while for cesium lead bromide, we are overestimating the band gap renormalization with respect to experiment. But if we start doing anharmonic special displacements on top of the polymorphous network, we see that we get very good agreement with experiment. And this comes as no surprise because the electrons will mostly likely want to see the nuclei in their ground state more probable configuration. And talking about polymorphic structures, the polymorphous structures are not unique. What is unique is the total energy, which is the minimum. But talking about configurations, there are infinite number of polymorphous structures. Here, another benefit of using the polymorphous structure. So if you go from the tetragonal to the cubic phase, and if you force the system to respect the symmetries of the structure, so going from the tetragonal to cubic, and you use a high symmetry system, you see you get a jump in your variation of the band gap with temperature, which is not the case in the experiment. However, if you account for local disorder and polymorphism in your calculations, you capture the smooth variation of the band gap with temperature in very good agreement with experiment. So some other applications of the special displacement method involve doing phono-assisted photocurrent in large solar cell devices, counting the charge density at finite temperatures, open circuit voltage. The methodology can be interfaced with GW calculations and hybrid fractionals. So here is a high throughput spirit calculation for temperature-dependent band gaps for perovskites or for other standard conventional semiconductors. The methodology can be applied on nanostructures. It's not only for solids, can be applied on molecules, nanostructures, and also can be used to obtain the phono-assisted spectra or more complex systems and phono-assisted emission spectra, as done here by the group of Kubakis in Michigan. So also another interesting application is that we can do optical spectra and incorporate the effect of xenophono coupling. So we displace the atoms in a supercell, and then we do a BSC calculation on top of that. So here we see that we can obtain xenophono spectra for the case of 2D germanium selenide, or X-ray absorption spectra in the case of hexagonal boron nitride. And here with electrophono coupling effects, we recover this double big peak structure that is observed in the experiment. Another very interesting application, basically this application says a lot about various questions that I get from the audience. So this is graphene, it's a metal material. Of course, we don't capture non-adiabatic effects, but still the methodology can be applied on metallic systems. And here's the example of electrical conductivity. So the authors of this work, they have applied the methodology to evaluate the optical conductivity. And we see here that by including electrophono coupling effects, of course, you get the renormalization of the electronic structure, and you get correct the shift that also matches if you apply this shift on the GW optical conductivity calculations to match the experiment, actually, and also the broadening of your conductivity. So another point that I want to say before going to the conclusions is that the methodology can be applied on pristine and doped systems. So it's agnostic whether you have doping or no doping, right? So take-home messages. The special displacement method is a very simple and efficient methodology for capturing both anharmonicity and electrophono coupling in ab initio calculations. So wherever you see blue on the presentation, if you download the presentation and click, you'll be directed to a link. Here you'll be so usually it's for the references, but here for tutorials and input flags, you'll get the link for the tutorials and input flags. not for today's school. This is the online tutorials. The SDM is not a simple numerical treat, but it encloses some important physics. So we have seen that if you do the special displacement, you can capture precisely diffuse scattering in systems. It has the potential to be upgraded to evaluate conductivity, tunneling spectra, exciton spectra, and also can be used for anharmonic phonons, and it compares well with the state of the art. Because anyway, those methodologies, they actually rely on the same principle and the same theory, the self-consistent phonon theory. And finally, would be like a nice potential application to interface temperature-dependent interatomic force constants with actual PW calculations and see how we can compute perturbatively using harmonic phonons the various quantities that you have seen in the school so far. I would like to thank you for your attention, my sources of funding, and here is a quick reference list, a small reference list for you to read if you are interested in the method. Thank you.
Thank you, Marius, for a very nice presentation. We have time for questions.
Oh, great.
Could you provide the slide every time? You said we could choose either the higher symmetry geometry or the lower symmetry one, which is the polymorphous one. So if we choose the higher symmetry, could we also obtain the quantities like electron-Phonon coupling and the anharmonicity?
So, can you repeat? Sorry.
Could we use the higher symmetry geometry to compute the electron-Phonon coupling with the special displacement method?
Yes, exactly. So this is, sorry, I went very quick here. So yeah, this is what we have demonstrated here. You can use, as long as you have the phonons, you can make a choice. Either you displace your atom starting from the high symmetry structure or from the polymorphic structure. So yeah, it's up to you. But what we are suggesting here is that doing it for the polymorphic structure is more accurate.
Thank you.
Can I ask, how do you actually get the infinite of the structure the beginning?
Yeah, I didn't discuss that. So to get the polymorphic structure, what we do here, so let's say this is the step 0 in the methodology, and you are going to learn that in the tutorial. So we compute the phonons of the monomorphic structure. We don't really care about if it's stable or unstable. And we displace the atoms along the soft modes initially. And we assume that these soft modes are populated at 0 Kelvin, 100 Kelvin, so you can change the temperature depending on the magnitude of the displacement. And then, because you force the symmetry to go far away from the high symmetric positions, then you can relax, and this will get you to the polymorphic structure.
And in that process, do you fix the volume, or?
Yeah, that's correct. So we fix the volume, we relax only the nuclei coordinates.
Yes, thank you.
Question?
Thanks for your talk. I have a question about the method in general. So when you calculate some observable its thermal average, how can you explain the physical insights behind this special displacement method? I mean, what I mean by that is usually in principle we need to calculate thermal weight and so on, like every member of the thermal ensemble. So you seem to replace it to one special displacement. So I'm just curious about the physical insights behind it.
The physical insight. I think I'll split my answer in two parts. So one thing that we need to have in mind is that the special displacement method is accurate with the supercell size, all right? But any method that you use, even if you do molecular dynamics in a 2-to-2 supercell and run a billion of configurations, or if you do Monte Carlo on a billion configurations, you are still in a 2-to-2 supercell. So you are limited in the phonon sample, right? So with the special displacement method for any supercell size, we try to provide the best approximate for that supercell size. And we try to minimize the configuration of sampling. Of course, for a 2-to-2 supercell, not for the harmonicity, but for the Electron-Phonon part, it might be not that accurate, the special displacement method. But still, the 2-to-2 supercell will never be accurate, all right? So now coming to the second part, for the physical meaning. So now if we imagine that you have a solid, all right? The solid is an infinite object of unit cells, all right? So if we have an infinite number of unit cells, we can capture all possible of, thermal vibrations in this object, and we can actually represent it with one configuration. And they have demonstrated basically the physical meaning, which is, for me, this is actually what gives you the physical meaning. Indeed, if we capture one configuration, we can precisely reproduce the thermal diffraction scattering pattern, the phonon diffuse scattering pattern that you see in the experiment. So that object seen in the experiment is seen also using one configuration. Thank you.
Three questions on Zoom. So the first one is, can this vertical rate be derived from Green's function theory? So can you sort of comment on the link between that and the framework that was presented?
So in general, okay, we rely on Rayleigh-Schrödinger perturbation theory. So we can link every quantity that we have in the special displacement method we have seen so far with a perturbative expression, but in the adiabatic form. For the Hertzsprung array, I think, indeed, someone can do a Green's function approach and have a similar expression. But yeah, here the spirit is, because we are in the non-perturbative approaches, we prefer to do the standard way for perturbation theory.
So there is another question about convergence. You sort of more insight about the convergence rate, in particular, there's is 888 and all.
Yeah, this is actually a very good question. So the suggestion is basically if you have the computational power and go larger in supercell, it's very good. And usually, so my experience is that if you're gonna go higher in supercell, you can play a little bit with the cutoff, all right? So you do a calculation for your cutoff, basically in a 444 supercell, and you reduce it. And you see what is the renormalization you get, or what is the temperature observable you get with a lower cutoff. So if your renormalization is accurate enough, then you can start going higher in supercell, all right? So in principle, someone should always check convergence with respect to the supercell size. In the literature, nobody really does that. So usually people, they use a 444 supercell, 55666, the best they can do, and they just show the result. Because sometimes it's impossible to go beyond that. For example, for the case of cesium lead bromide, I had to include also spin-orbit coupling in a 4x4x4 supercell. So if you have 500 atoms, spin-orbit coupling, a large cutoff, and you want to claim accuracy, the best you can do maybe is 500 atoms. But if you don't have spin-orbit coupling, maybe you can go 1,200, depending on, if you reduce the cutoff, you might be able, and use gamma point only, you might be able to go up to 2,000 atoms, but that's all.
Somebody is asking about your polymorphous network. Specifically, is it possible that one of the polymorphous network has negative phonon, or the theory assumes that any polymorphous network will always be the most stable configuration?
Yeah, the question contains two information. two pieces of information, sorry. So indeed, the polymorphous structure, if you have a large enough supercell size, should get you to the ground state of the system. Here we do one, not trick, it's physically justified. So what we do for the polymorphous structure, if I just compute the phonons of this polymorphous structure, I might add some instabilities because of the supercell size. But what do we do here? We enforce the symmetries, and this is not something that comes out of my head. It's because the polymorphous structure macroscopically should respect the symmetries of the lattice. So if you enforce the symmetries, you speed up convergence towards the stable solution for the polymorphous case. And the second question was, it's two parts, I think, the question. Okay. Yeah, okay.
And maybe the last question, so it's asking is your teaching method also implementable or useful for lattice thermal?
So that's the point. So for computing thermal conductivity, you need to get information about the third order interatomic force constants. For sure, someone can compute using the special displacement method, but I think it's not the way to go. The way to go would be like, there are implementations like in Alamode where actually it's very, it's a robust methodology where you can actually compute third order interatomic force constants. You use the perturbative expression, and you get the thermal conductivity. But yeah, here's the goal was basically, so with the special displacement method, you can obtain other quantities like heat capacity, for example, but let's say not the thermal conductivity.
We have time for a few more questions.
Hi, could you explain one more time, because this time, what the criterion is for selecting that special displacement?
Okay, so you remember the linear coordinate transformation expression we start from the beginning, all right? So the rest, so I can just tell you to look at this equation here, okay? This is the simplest version, all right? So here we have, basically here, if you do the Taylor expansion, do you remember the Taylor expansion with respect to normal coordinates? So you have all this xn prime, blah, blah, blah. So we do choose, because of the Williams-Lack theory, it's very trivial to choose xn equals this sigma, okay? Very trivial. I mean, it's here. The answer is here. You just do this integral here, very quick, like first year undergrad, you get the integral, or even high school. Then you get this this expression here. Then you decide that xn equals to sigma n, and then you have these cross-coupling terms. You want to kill these cross-coupling terms. And coming now to merge the whole thing together, if you do a reciprocal space formulation, these cross-coupling terms for a different wave vector, q wave vector, they die. And what you are left is only with cross-coupling terms between different branches. And you want to kill these cross-coupling terms. You want each of the cross-coupling terms to kill each other. So you just do plus, minus, plus, minus. But if in the reciprocal space formulation, because the problem is quite different, so you have a different matrix of signs, you do combinatorics with the restriction that you have basically the same number of positive signs and negative signs, and you can, by minimizing this error fraction, you can reduce the error. But as I said before, it's not only reducing the error within the supercell size, but it's also increasing the size of the supercell. Because by increasing the size of the supercell, you capture more phonons in your calculations.
You mentioned that at some point, SDM method can be applied to the excited phonon coupling, right? So is it going to be available in the course soon, or what's the plan?
So that's just it. So you don't really need to have something, a tool for that. So you have the tool of generating the special displacements, right? So once you generate the configuration, the procedure is exactly the same when you when you did yesterday Berkeley's W and you did a BSC calculation, so instead of using a unit cell, now you have a supercell, and the difficult part is that it's very computational demanding. So that's why sometimes like perturbation theory, it's better. But if you have the computational